Hey all, good morning. Welcome to ShareTreck. This is your host Raj here. Today is the 12th of March 2022, and I had a great surprise when I woke up. There are around 230 subscribers. So thanks for all the new subscribers for joining us, and it encourages me to try and improve our videos out here and the content and the quality. You may notice that of late I have 4K videos out. So that's in terms of video quality, but even in terms of the content, it encourages me to do a little bit more research and get more information to you. So thanks for subscribing. Let us get that out of the way first. And then I would like to talk to you today about some of these terminologies that have been bouncing around our heads for a while. And I don't know about you, but as a non-science person, my background is in business and technology. I always found it a bit confusing between CRISPR-Cas9, base editing, prime editing, CAR-T, how they are all related to each other, and what does it mean to me as an investor in a particular genomics company. So today I thought of putting that across to you and defining each of these to the best of my abilities and comparing and contrasting them to show how they fit together. So that we can look at our genomic investments in a different light and understand what it means and what it does not. Let's get started. Let's first get started with the CAR T cells. CAR T cells are human immune cells known as T lymphocytes, which have been modified. They have been genetically engineered to express a chimeric antigen receptor, that is the CAR, and that's an artificial receptor that can recognize specific types of cancer, and genetically altering T cells to express a CAR enables the immune system to target and destroy cancer cells. So that's a summary of how CAR T cells are explained. If you see the amateur drawing that I have done here, you can see two figures out there. One is the cancer cell, which is on the left, and on the right you have the CAR T cell. So the fork-like appendages that are there on the CAR T cell are the ones that are induced by genetically engineering them. And there are two ways in which this therapy can be done. In the autologous approach, what happens is the clinicians first identify the specific antigen produced by the cancer cells in the patient. And having identified that, they make a note of it because they have to now design a chimeric antigen receptor that targets those antigens. Next, they extract blood from the body of the patient and genetically alter the T cells by giving them a chimeric antigen receptor that would target that particular antigen, and then they put it back into the body of the patient. And once inside the patient, the altered T cells, which are now CAR T cells, will zero in on the antigens wherever it can find them and destroy those cancer cells. So that is the mechanism by which CAR T cells operate. And it can also be done in an allogenous method, where instead of taking blood from the patient, the blood could be taken from a compatible donor, a healthy donor, and then modified and put back into the body of the patient. But there is a bit of a difference in the outcomes. The risk factors are slightly different. Autogenous approaches are more conducive to the body accepting the modified T cells much easily. The CAR T cells can easily get into the body and evade the immune systems and do their job. Whereas if you were going in for an allogenic approach and the T cells are coming from a donor, then there is a chance of something called as GVHD, graft versus host disease, where the immune system of the patient starts recognizing the T cell as an invader, and there is a conflict out there. So those things needed to be avoided. However, on the flip side, the allogenic approach is much stronger because the T cells are more robust and healthy, whereas in autogenous method, there's a chance that the T cells from the patient might be weak to begin with and therefore may not be as effective. So this is what the CAR T cells is all about. CAR T cells have been developed even before CRISPR came into play. So there are other gene editing methodologies that can be used to create CAR T cells. So that's how CRISPR-Cas9 is related to CAR T. You can use CRISPR-Cas9 to create CAR T cells, but there are other gene editing technologies that are already being used to create CAR T cells. So that's where one of the epiphany I had was, okay, CAR T cells can be done without CRISPR-Cas9. And you can also use CRISPR-Cas9 to create CAR T cells. So just to recap the key points for CAR T, you can have CAR T therapy either autologous or allogenic. CAR T can be made using CRISPR-Cas9 or other gene editing technologies. The most important point is that CRISPR is a gene editing technology and a tool, whereas CAR T cells are products created using CRISPR or other gene editing technology. CAR T cells predate CRISPR. So this is what we need to remember as investors. And if any of the viewers of this video are scientists who are working on CRISPR-Cas9 and CAR T, etc., if you find anything that needs to be improved in the definition, please put it in the comments below. And I would put it on top. I would pin the comments up there so that this is a much more accurate presentation for most investors. So let's move on to the next topic, which is going to be base editing. So base editing is a CRISPR-Cas9 based genome editing technology that allows the introduction of point mutations in the DNA without generating double-strand breaks, which is called DSB in the business. So far, only two major classes of base editors have been developed. The first one is CBE or cytidine-based editors, allowing converting C to T, and adenine-based editors or ABEs, allowing A to G. So that's the extent of base editing. The difference between conventional CRISPR-Cas9 editing and base editing is that the former uses double-strand breaks, while the base editing avoids double-strand breaks and works as a single-strand base conversion. The problem with conventional CRISPR-Cas9 is that it introduces double-strand breaks and risks introducing many random insertions and deletions. And also the body's overzealous cell repair systems might try to patch the CRISPR-generated double-strand breaks and introduce more problems there. And one of the main risk factor is that if cancer cells end up getting involved in the repair mechanism, then it will be replicating cancer cells at a much faster pace. And other irregularities can happen. So that's one of the problems with CRISPR-Cas9 that is avoided by base editing, because there is no double-strand breaks out here. And base editing molecular components are, however, much bigger than CRISPR-Cas9, and therefore delivery is a challenge. So where there's a benefit, there's also a challenge. So, and again, as you can note that only C to T and A to G conversions are possible. So that's also a limit on the therapies that can be developed or the diseases that can be targeted using base editing. However, base editing is much more precise and much more efficient, and off-base edits are significantly reduced, and editing is absolutely to the target. So that's the benefit of base editing. Now we come to another term, terminology, which is prime editing. So let us see what prime editing is all about. Prime editing is superior to base editing and combines a modified Cas9 enzyme with another that can generate new genetic code. They are shepherded into the target DNA by an RNA guide, and once there are designed to permanently edit a mutation or other genetic defect. To a great extent, this is similar to base editing, but unlike just two classes of base editor, we have all 12 possible transition and transversion mutation, as well as small insertion and deletion capability in prime editing. That's what makes it superior to base editing. And prime editing makes some notable modification to traditional CRISPR-Cas setup. The cutting enzyme Cas9 has been modified to only cut one strand of DNA. The guide RNA diploid also contains the instructions for the desired edit, and a second enzyme called reverse transcriptase has been added to the payload to write the desired edits into the exposed strand of target DNA. So those are all the mechanisms. And as investors, it would make very little sense for us reading all these exotic methodologies and terminologies out here. But suffice to understand that with base editing, we have got only 2 alphabets that are being targeted. And with prime editing, we have got the entire set of 12 alphabets. So there's a whole range of editing possible with prime editing. So then the question becomes, how is base editing still useful, and where do we use prime editing? Would prime editing completely replace base editing? So that brings us to the advantage and disadvantage of prime editing. So prime editing is not limited to PAM adjacent targets, and true search and replace is possible without off-base edits when it comes to prime editing. And the disadvantage is the large size, and it's a very recent development, and therefore it has been tested only in 4 to 5 cell types. And from my reading on this topic, I believe that one of those 5 cell types is related to mice. So it's a very limited cell type that have been tested on with prime editing. So there is a lot of work yet to be done with prime editing for it to become much more potent. Right now, base editing has had the maximum amount of work done on various kinds of cells, and it is still a leading candidate for therapies. So we'll have to wait a little bit for prime editing to mature. And of course, then it will open up a wide range of therapies for a wide range of situations. So that brings me to my next topic, and that is around a new development that has taken place under the leadership of Dr. Marson in Gladstone Institute and UC San Francisco. They have introduced 2 new tools called CRISPRa and CRISPRi. The A at the end of CRISPR and the I at the end of CRISPR stand for activation and inactivation respectively. So what they have done is they have taken the Cas9 protein and modified it so that instead of it cutting at a specified point, it would take a molecule that would activate or deactivate a gene on binding to the location. So when CRISPR has got an activating molecule attached to it, it's CRISPRa. When it has got an inactivating molecule, it's called CRISPRi. Using these two and adapting it to the human immune system, Dr. Marson's team is trying to create a Rosetta Stone or a dictionary of how the immune system functions. So now let me pull together all the threads of this video so that we can come to some conclusions. So when we look at base editing companies, which is the technology that we spoke about, we distinguish CRISPR-Cas9 and how base editing differs from that and how prime editing differs from base editing. So now let us pull it all together. The base editing company is basically Beam Therapeutics, to the best of my knowledge. I don't think anybody else is doing base editing. If any of the viewers of this video know of any companies other than Beam which are doing base editing, please put in the comments below so that I can be enlightened and I can use that in my further research on this topic. The other company that is involved in prime editing is Prime Medicine, which is a new startup. In 2021, they got funding of $350 million, and they focus only on prime editing. And both Beam and Prime Medicine have some shared alumnus, and they have an understanding to optimize their work so that they don't do the same research and duplicate the efforts. So that's the scoop on Prime Medicine. Prime Medicine, I'm going to do more investigation on Prime Medicine and bring information to you. I don't think they are in the share market at this point of time, so we have to watch for an IPO in some future date, or maybe Beam will have other ideas with Prime Medicine. We don't know. We need to find about that. So that's about the companies which are involved in both prime editing as well as base editing. In terms of conclusions, I would like to say that there is a lot of investor enthusiasm in the CRISPR space, which is reflected by the fact that despite really horrible market environment, there are still people who are buying CRISPR stocks. There are still people who are holding CRISPR stocks and dollar cost averaging down. And also the fact that so many of you are looking at my channel here, which is focusing only on CRISPR, and we are growing in numbers, indicates that there is a lot of investor enthusiasm in CRISPR. So that's a very good positive. And the challenges still remain. The challenges are in terms of capability to deliver it into the body, because these molecules are large. So that's one problem. Second problem in terms of delivery is off-base edits. So that's another problem that needs to be sorted out. There are other challenges with regard to countering the human immune system. Right now, there is radiation and chemotherapy, which is also a precursor to most of these therapies that we are talking about here, and they reduce the efficiency of the therapy. So we need some alternative method to suppress the immune system to accept modified molecules and modified cells to do their job much more effectively. So those challenges still remain. And also we have the possibility of ex vivo therapies being much more successful than in vivo, basically because of all those problems that I mentioned earlier, the larger size of the molecule, the fight with the defense mechanism of the body, and all those aspects. So ex vivo at this point of time seems to be a better therapy for success as compared to in vivo therapies. Base editing tools seems to hold a better promise than CRISPR-Cas9 or even prime editing at this point of time, because it is very specific. It doesn't do double strand editing, and therefore chances of other problems happening is diminished significantly. Much more precise, much more surgical in its nature. So base editing is much preferred at this point of time and has better promise. Prime editing has got a lot of potential, but it has to prove itself because it's a much more recent development, and it has been worked on only 3 or 4 cell types. So we need to have much more cell types to be worked on with prime editing before it can attain the same potential or better potential than base editing. So in my opinion, we as investors need to actively follow the development and keep on learning the lexicon and understand the mechanics, not as scientists, but at a level as an investor. We need to be much more involved in this than we would be for maybe a share like Shopify or Amazon. The kind of knowledge that we need here is much more deeper. So this field is likely to attract more technocrats with much more interest in actually understanding the way the cells behave and way these technologies are being developed. So the class of investor that can invest successfully in this field is the one who is willing to invest more time and efforts in following the developments and understanding the mechanisms, so that you can evaluate for yourself what the risks are and what is the monetization horizon. From my point of view, after looking at all these things, I think the monetization horizon is at least 3 to 5 years away, and there is much more to come. We are still in the baby stages, so we need more patience. And right now, given the market conditions, I think we are ripe for dollar cost averaging. But personally, I would prefer to dollar cost average on my way up, because these therapies have fallen down drastically. But I also have the fear at the back of my mind that when it starts going up, there's a good chance that it may be a rocket just boosting off on market open. So those risks are also there. So let us continue to pool our knowledge and understanding. I would encourage all the viewers to put your remarks in the comments below, so that you can guide me to look at specific areas which I might have a blind spot to right now, so that our future videos are even more effective and more informative. So thanks a lot. I hope you have an enjoyable weekend. Look out for my Sunday video, which is coming tomorrow. And please put a like here so that more people can see these videos and come to our channel. And if you're here for the first time or have been watching these videos for a while, please subscribe. It's absolutely free and help us grow this channel. Thanks and have a great day. Bye for now.